record when seminar for spring 2022. This is a special one because this is also jointly organized by the AI Institute for Resilient Agriculture at Iowa State, as well as the NSF CPS Frontier project called Coalesce, and that's also a joint project between Iowa State and UIUC. So we're extremely happy and privileged to have Professor Oliver Kremer as our speaker today. Oliver is an assistant professor at CMU Robotics Institute, where he leads the Intelligent Autonomous Manipulation Lab. His research focus is on developing algorithms and representations to enable robots to learn versatile and robust manipulation skills. Before joining CMU, he was a postdoc at USC for a couple of years. And before that, he received his master's and bachelor's degree in engineering from University of Cambridge in 2008. And between 2009 and 2011, he was a PhD student at Max Planck Institute for Intelligent Systems. And finally, he defended his PhD on machine learning for robot grasping and manipulation in 2014 at TU Darmstadt. So with that, Oliver, the floor is yours.
Thank you for that introduction, and thank you everyone for joining. I'm happy that so many people can show up. So today, the topic is going to be fairly broad. It's going to be talking about structuring manipulation tasks for more efficient learning. And before I sort of jump into the presentation itself, so this is kind of the first IRA sort of presentation we've had. So I just wanted to mention a couple of things. So first of all, my talk is going to be sort of looking at general manipulation problems. For me, agricultural domain is something a little bit new, so something I'm excited to be exploring more of, and sort of the challenges of clutter and occlusion, and sort of working with deformable objects. So keep that in mind. The most important thing, though, is that I want this talk to be a little bit of a basis for potential collaborations. So please feel free to jump in at any point in time to ask questions or start discussions. I have more than enough slides to cover an hour, so I'm probably not going to reach the end anyways, and I would love to sort of be able to talk to people about some of the challenges. I've also added a couple of slides that are sort of green, like this one, which I call my new growth slides. So these are kind of areas I'm currently working at, or would love to sort of discuss in more detail, or for if there's people interested in collaboration. But obviously, if there's other aspects of my research where you think, oh, this would be great, I'm sure there's many problems I haven't thought about where it connects to the larger area of agriculture and agricultural robotics. Then please do let me know. All right, so getting to the actual presentation. So in the future, we obviously want robots to work on a wide range of different application domains. So we want robots that can work in our homes and hospitals, warehouses, the fields, and there's a lot of challenges in getting robots that can actually perform manipulation tasks in these different places. So until now, there's been a lot of focus on applying robot manipulation in domains where we have structured environments, such as manufacturing, especially if it's very repetitive motions. And in order to be able to have robots deployed in larger areas, so for example, pruning plants that are very unstructured, or placing sensors, we need robots that have both robust and versatile manipulation skills, right? So robust in the sense that they need to be reliable when we execute them. They need to be able to, do what they're meant to do. But they also need to be able to detect errors, make sure that they're not trying to perform actions in situations where it's not feasible. So maybe a stock is simply not large enough for some kind of interaction, then we shouldn't do that. And we also want skills that are versatile. So if we provide the robot with all these different kinds of situations, that the manipulation skills it has can adapt to each of these situations accordingly, and take into consideration things like, changes in objects, changes in material properties, changes in the configurations, and do that in a way that, we don't have to relearn for every single situation. So a lot of my lab's work is really focused on this idea of learning robust and versatile manipulation skills. So if we want to sort of take this, very challenging domain and we want to make it somehow tractable, and let's consider the task of a robot cooking, right? So preparing food. Here we have a peer or two, cutting like a cucumber. And obviously it's a very, cluttered environment. You can imagine if this was an actual kitchen, it would be even more cluttered. There'd be more objects, and the problem can seem very daunting, right? And so one of the aspects I'm going to be talking about is this idea of scope, right? Of sort of identifying what are the regions where we really need to focus in on, what are the relevant objects in these scenes, and when do we actually need to use sort of learning, or when can we sort of fall back on more sort of, model-based reasoning approaches. So the first, one of the topics is going to be looking at scope. Another important aspect for making these really challenging problems tractable is modularity, right? So how do we sort of take a big problem and break it down into small components that we can reuse between different situations? So for example, here we have, the robot has its hands. Obviously, ideally, you can switch between left and right-handed robots. We have different food items. So if we wanted to cut a different vegetable, such as, a bell pepper, we would be able to switch out the bell pepper, the bell pepper for the cucumber fairly naturally, without having to relearn an entire skill for doing that. Or if we have, a different kind of knife, we'd be able to change that out as well. And thinking also about the kind of interactions. So, if we grasp an object, so, the grasp we're using here for the cucumber is fairly similar to the grasp we're using for the knife. And so again, being able to share that information is very valuable and makes the problems a lot more tractable. The last area is going to be interaction. So one of the great things about having robots is the fact that they can actually interact with their environment. They can, apply different actions. They can effectively apply tests to the environment, see what the response is to those tests, and use that information to get to get a better understanding of the world around them. So, for example, we might detect the fact that when we're cutting down, when we actually hit the cutting board, we get sensory information from that, telling us that contact state has changed, which might be very difficult if we just do it visually. If we have, bell peppers and a plastic toy there, again, visually, they might look very similar, and we might obviously treat them as separate objects. But when we interact with them, we can get additional information about maybe this is actually a plastic toy, and therefore it's not actually suitable for this kind of cutting task. All right. So to begin with, I'm going to actually jump into interactions here on the right. And we're going to talk about vibrations, actually. So this part is going to be interactions, or how to get the most out of good vibrations. So whenever I think about a manipulation task, one of the first things I always think about is manipulation modes, or different kinds of contact states between objects. So here we have a human hand grasping an object. It's obviously a very simple task, something that we do every day. But what's interesting is we can sort of decompose it into these distinct modes. So in the first mode, our hand is sort of, reaching towards the object. It's not made contact with it. The second mode, we've made contact with the object. At this point, if we try to move our hand, we're actually applying forces to the object. And then we can either choose to sort of, apply enough upward force to actually break contact between the object and the surface, or enough sideways motion to actually slide the object. And one of the key characteristics about these modes is that depending on which mode we're in, our actions are going to have different effects, right? So we're going to move our hand, we're going to apply forces to the object in the middle here, or we're going to actually move our hand and the object together in space. Another important aspect about manipulation modes is that they help to define sub-goals and errors, right? So if I wanted to pick up this object without scraping across the surface, or without damaging the surface, then this transition over here to the right would be seen as a sub-goal, and this one down here would be seen as an error, right? Similarly, we could sort of say if I want to, scrub this surface, then this becomes a sub-goal and this becomes an error. Another important property about modes, and the one I'm going to be focusing on in this case, is actually that they often correspond to changes in contact, and therefore also correspond often to very characteristic kinds of vibration signals. So for example, when we transition from our hand not being in contact to making contact, we get small vibrations being created there. If we pick up the object, we get vibrations from the breaking of the contact. And obviously, if we slide this object across the surface, then we're going to get a lot of vibrations from that sort of scraping sound, right? And I'm sure some of you are looking at this and can even imagine what that sound would look like, would sound like between this wooden block and plastic bucket. And so, this has been fairly widely studied in grasping, but it's very broadly applicable, right? So we also get these kinds of modes when we're thinking about something like cutting. And so my lab is very interested in this idea of sort of cutting different vegetables. So here, for example, we go down, we can detect when we make contact with the object. We're then going to sort of cut through until we detect when we actually make contact with the bottom. And then, at that point, we can move on to the next slice. And we can also detect things such as when the knife sort of slides off of the object. So if we try to go for a very thin slice, we can detect those errors. So there's a slip detection. And so we can sort of, detect when we have the different modes and use those to switch between different contacts. And we use a couple of different sensors. So we have a camera looking down at the scene. To be honest, that one's not too useful for these kinds of mode detections, especially given the fact that, we have shiny knife and stuff like that. But what we also have is we have contact microphones. So we have a microphone back here on the tongs. We have one here on the knife handle, and we have some underneath the cutting board. And those are really listening for those vibration signals when we have the contact switches. All right. So when you sort of start scraping across the surface, you can detect that in the the cutting board. When you make contact going down, you can hear that in the microphone for the tongs, and so we can use those for those mode detections. What we can also do is we can use these sort of vibrations to give additional information about the materials, right? So as I mentioned before, a lot of you can probably imagine what this sort of sounds like, especially when I tell you it's wood and plastic, that kind of a scraping interaction. And we want to do the same thing for food, right? So effectively what we're looking at is when we first make that downward contact with the food, right? We detect that, we've made contact, we need to stop, but we also collect about 0.1 seconds of vibration signals, which we want to use to classify the different types of food. So here we have 25 different kinds of food that we explored in this project. Some of them are obviously very visually distinct. We don't actually use vision for this. We are just relying on vibrations. And we do have some that are very similar. So we have, for example, cucumbers versus zucchinis, which visually look very similar. We also have old cucumber versus a cucumber. If anyone was wondering what the student definition of an old vegetable is, it means it's been in the fridge for a week. We also have things such as frozen lemons, and oranges that we want to be able to separate, or cheese and onions and tofu, right? And the way that we actually do this classification is we take those 0.1 seconds of information where we're going down. So before we do any kind of back and forth motion, and we compute what's known as the melt frequency cepstrum coefficients. So if you think about the audio signal, taking the power spectrum of that, or the Fourier transform, and then treating that Fourier transform as sort of, or the power spectrum as a signal, and applying another power spectrum on top of that, you get what's known as these cepstrum coefficients. Intuitively, the cepstrum is often thought of as sort of the timbre. So it's looking at the harmonic structure of the underlying audio signal. And so if you have, for example, a woodwind instrument and a brass instrument playing the same note, so the same main frequency, The harmonic structure afterwards is, is going to be different because of different items, the different instruments. And that's sort of captured by the timbre or by these sort of Sedstrom coefficients. And in our case, rather than brass and woodwind, we have cucumber and lemon effectively. But the logic is kind of, or the intuition is very similar. With these, we can sort of train a classifier. In fact, it's a very straightforward classifier. We've got 3 fully collected layers, 100 units each, and we just output these 25 different food classes. And here you can see the confusion matrix. It's obviously not 30 by 30. Here we're actually only showing the errors. So we actually get a very high F1 score of 0.9915. So we get very good classification performance. We do get some mistakes. So for example, watermelon and a frozen lemon are sort of confused. Again, we're not using visual. So obviously if we used visual information, those kind of errors could also be avoided. But we see that these are very rich signals. They are fairly structured, so we are kind of always moving down for robots. A very similar behavior every time, so we're not getting a huge variability of the types of interactions that we're seeing. But it's definitely a good performance for this kind of a task. So we can also do then is we can provide the robot with some demonstrations. So here we have a student. I should mention there is another student off screen with their hand on the emergency stop. This is in a compliant mode. But he's effectively giving demonstrations of sort of a cutting behavior. And so we can sort of provide the robot with these sort of parameterized skill representations known as dynamic motor primitives. Here you can effectively see the back and forth motion in the X direction, not a lot of movement in the Y direction, and sort of this gradual going down the Z direction. And what we can do then is we can effectively set the amplitudes for each one of these vegetables for both the X and the Z. So we take that initial demonstration and we're going to adapt them to each of these types of vegetables. So for example, for tofu, you don't need a lot of back and forth. You can just go down. A couple of objects were not possible. So the corn and the spaghetti squash simply can't be cut, although we can still classify them. What we can then do is we can actually have the robot, go down, classify the object, and actually choose the corresponding parameters. So for example, here you can see that the carrot cuts through quite quickly. For the old tomato, it needs a little bit more back and forth because the parameters are sort of to give a very gentle motion, so we try not to damage the old tomato. There's something in the chat. Is there a distinction in the force curves when a novice produces these forces versus a chef produces them? So we haven't had a chef actually give the demonstrations. There has been some work at CMU looking at sort of the force profiles. What we have done is we've done some reinforcement learning. Unfortunately, that's not as quite in the slides. I think I might have some backup slides on it, where we tried to do sort of human in the loop learning, but we haven't really compared a novice to a chef. That's definitely something that would be interesting to do, and to sort of see what the difference in the underlying reward function might be. I think in some cases you might also get some behaviors that are outside of robot capability. So if you're doing very fast chopping, really using the elasticity of the human arm, that's something that we might not be able to do on the real robot. But I agree, looking into a chef would be fantastic. All right. Okay, but so these are, you can see that it is adapting to these different kinds of food items, and we have a clear classification. So it is actually, doing that task well. What I really like is that if we actually apply this to new vegetables and fruits. So for example, here we have a peach. It's not a very ripe peach, so it's a little bit, maybe a little bit early to eat it. But what we can see is that we have these, it's a peach that hasn't seen a peach before, but it does know what a zucchini is. And so it's sort of identified that the properties are fairly similar to those of a zucchini, and it'll keep sort of cutting through it. If it hits the pit, it's not in the video, it'll actually stop because it thinks that hit something. Down here, we have a pear. So a pear is obviously very similar to an apple. So it's kind of, again, it doesn't know what a pear is, but it can classify it as an apple and then just transfer over those parameters. My favorite is probably this one down here in the bottom right. So in this case, visually, a jalapeno and a bell pepper are fairly different. Bell peppers tend to be much larger. But as we all know, they have this nice sort of, juicy cell structure. And so by sort of making that initial contact, it detects that, okay, the material properties are actually fairly similar to a bell pepper. And so it's going to cut it as a bell pepper. Obviously, the fact that it's much smaller, it's going to hit the board earlier, but we have that, that contact detection as well. So it'll terminate at that point when it reaches the cutting board. So that project looked at, how we can do it for cutting, and we were very interested in sort of exploring further this idea of using interactions to learn useful representations of objects, and also, incorporating things such as this tactile sensing. We were very interested in this idea of also children sort of, playing with food and learning about their environment through these kinds of interactions, right? So kind of a self-supervised learning through play so that we get a better understanding of the objects that we're working with in our environment. So in this next project, we wanted to learn visual representations, but we wanted to learn them from interactions. And to do this, we had the robot effectively play with some food. Okay, I think that might have just been an accidental unmute. Do let me know if there's any questions. Do feel free to raise your hand or just jump in. All right, so effectively what we had the robot do is we have these sort of sensorized fingers. We have got cameras in the middle. Again, we've got microphones on the back. We have microphones underneath the surface as well. So we can get nice rich vibration signals again. We had the robot grasp the food items, pick them up, drop them, and also push down on them. So yeah, our modalities are vision, vibration, and proprioception. So we also get some force estimates, or I guess I should say haptic feedback from the arm, as well as things such as the distance between the fingers when we're sort of closing our hand. And so, we looked at a variety of different food items. I think it was 20 overall. Lots of different slices. We also had the robot creating the slices, so we knew which kind of slicing parameters, so which angles it was using to create them, so it can use that as well. And obviously, here we have a whole bunch of different objects that it played with, and at the end, after playing with it, some of them look a little bit less appetizing. But it's interesting to see sort of, the kind of deformations we can see here. So things to kind of point out are things like, potatoes. If they're large chunks, they're effectively rigid. They're not going to move a lot. Maybe a little bit of a crunch when you squeeze into them. Whereas when they're small, they become a little bit more brittle. They actually kind of snap in the fingers. Some things like the Spam just kind of crumbles. We have multiple ones with sort of peel on them, which kind of get a little bit dejuiced during the process, but still have that sort of tough outer side. So what we want to do is ultimately still learn a visual representation, right? So if we now have a chef robot, we obviously don't want it to be playing around with the food to the point where it's not that edible looking, or still edible, but not as appetizing. There's the word. And so what we want to do is we want to learn a representation of the visual information in a way that we can then apply different kinds of classifiers to those representations to do things that detect or predict hardness or juiciness, which we might need for our manipulation skills. So the way that we do this is using a triplet loss. So we have this embedding network that takes always one image at a time. So here, for example, we have a tomato slice, and it's going to map that to an embedding vector. And we train it using a triplet loss. So that pretty much means that we always have one sample, sort of an arbitrary sample in our data set. And for each of these anchors, we have a positive sample. So that's something that should be similar. And we have a negative sample, which is something that should be further away. And effectively, the training tries to make it so that the embedding vector between the positive and the anchor are close to each other. and the anchor and the negative are pushed further apart, okay? So we sort of get this a space where things that should be sort of similar are close to each other, and that are further away are pushed apart. The key problem here is, how do we get the sort of labels of positive, anchor, and negative? And this is where our additional features from the interactions come into play. So we can look at, for example, the Cepstrom coefficients of two slices being sort of played with, and we can say, oh, these are actually fairly similar, so we're going to consider those as positive and anchor, or these two are very different, so these are going to be anchor and negative pairs. And so we effectively use those interactions to get this information for creating these positive and anchor negative, which we then use to train the triplet loss. And then once we have that embedding, we can apply a classification problem on it. So in this case, these tend to be sort of human labels, but for a small set of data, which we can then leverage these better representations. All right, so here you can see the results of this. So we had a couple of different classification problems. So for example, the first one is simply the food type accuracy. So in this case, we had 21 different classes. We also looked at things such as the hardness, where we had hard, medium, and soft. Juiciness. So obviously, if you want to replace some kind of a fruit or vegetable in a meal, you might want to have something that's similarly juiciness. Slice type. So how did the slice was actually given from the image, and also the slice width. So if we actually grasp it, how much space is there between our fingers? And at the bottom, we have two sort of baselines. We have ResNet, which has obviously been trained on a lot of different pictures, a lot of different food types included in that data set. We sort of fine-tune it just for this data. We also have a classifier that's directly using the audio data from the play. So in the same way as we did it for the modes and the material classification, we can simply use those, that audio information. Obviously, we couldn't use that if, when we're actually trying to cook something delicious. But just as a baseline, we also include it here. And up here, we have sort of these embeddings that learned with different information to create the triplet. So we have the food type, we have the slice parameters, we have the Cepstrom audio features from the playing, we have the audio features from the creating the cut, we have proprioceptive feature, and we have the concatenation of audio play and proprioception. And what we can see is that, okay, for food type accuracy, obviously ResNet performs the best. It just has a lot more data. There's nothing really about the name of a fruit that manipulation is really going to help you out with. But if we look at, for example, the hardness, we see that in this case, the proprioceptive data, so pushing down on it and seeing how much force or how much it sort of we can push down on it or how much we can squeeze it. Learning the embedding from that actually gave us the best performance. Similarly, for juiciness, we see that the data during the play was sort of giving us the best performance. And so you can imagine that you are going to get some watery sounds in there for the more juicier ones. So that can obviously be very useful. And for the slice type, actually using the slices to actually as embedding was also so useful. And then, slice width, again, this is proprioception. So we get this a fairly natural sort of, mapping of, okay, these are kind of properties we might want to learn and predict, and having sort of embeddings based on those kind of interactions can be very useful. Another thing I want to show, this is actually embedding learned from audio features of play for boiled objects. So we took some of the vegetables and we had both before boiling and after boiling. So the circles here, these are pre-boiled, and these little line shapes, these are sort of after boiled, and then the color indicates the kind of vegetable. And so we have, for example, apples and pears. This is the yellow and the pink. We can see that in this sort of lower dimensional embedding space, they're already fairly similar to each other at the beginning. And when we boil them, they make the shift over here, where they're still fairly close to each other, but now obviously in a boiled state, so a little bit more juicy, a little bit softer. What I find really interesting is the carrots and the potatoes, so the orange and the brown. So originally, these are a little bit separated. So you have the carrots more up here and closer to the celery, I guess. And we have down here the potatoes, which are brown. And if you have raw carrots and potatoes, they can be a little bit different when you start interacting with them. But if you boil them, they actually get a little bit more a similar texture. In Germany, we often sort of do sort of a mash between carrots and potatoes, which is very yummy. And the boiling kind of softens them both up and gives them more similar texture. And we can actually see that they're also kind of mapped to a more similar location in this embedding. And so I'm always fascinated by the fact that the embedding sort of learned that kind of a consistency or intuition almost. All right, so looking at learning from interactions, some of the key takeaway messages. First of all, I would always say try to exploit variable tactile feedback. It's a super cheap sensor modality. It's very rich information, both about contact states and also about different kinds of material properties, as we saw here. And it's also important to think about using interactions as a basis for richer representations. And in particular, this idea of sort of interactive learning. So we can think of it as sort of interactive perception being when we perform actions and we directly get information that we're going to use for that object we're interacting with. Interactive learning is sort of this idea that we take that information we learned and now we're going to use that for learning to predict properties of other objects in the future, right? So as we saw here, if we now show a tomato slice, we don't need to interact with it. We can just have the input, get the embedding of it, pass it through our classifier, and then make the prediction. And we sort of learned in the past while the robot was playing with food, right? And that's very similar to how humans kind of learn about their environment by playing with food. And then later on, we have a much better idea of the kind of food that's on our plate without necessarily having to, pull it apart and drop it and grasp it. All right. So in terms of the new growth and sort of how this sort of extends a little bit into what we're working on now. So part of the IRA project is to sort of place sensors for monitoring plants. And we want to be able to place sensors on leaves, on stems, so sort of insert them into stems, and also put them into the soil. And so in order to do that, really need to make sure that we have a suitable contact with our environment. If we're placing something on a leaf, we want to make sure that we have a good contact with the leaf. So we want to make sure that we can classify whether or not we've made contact with the right object using some kind of vibrotactile feedback. And obviously, we don't want to sort of, we just actually got these sensors from Liang in the mailbox on Wednesday. So Liang, thank you for sending those if you're on the call. We're really excited to start working with these and sort of looking at how to sort of place them. But obviously, we can't sort of add additional tactile sensors onto these sensors themselves, which are going to get in the way of the readings, right? We don't need to stick a tactile sensor into a stem, but we rather just want to be able to detect whether or not we've made contact with a stem. And so we're looking into sort of using the vibration signals in order to classify different parts of the plants. So here's what we're currently working with. So we have this sort of probe we've designed for creating a data set. So we have a sort of plastic head, which is going to be used for interacting with the surfaces. Obviously, we might have to adapt that a little bit once we go for something like what the gripper will look like for actually placing the sensors. But we have a forward camera, we have an observing camera looking at the scene around it. We have a force torque sensor. We have an array of different microphones along the side. We've also recently added Vicon markers onto this sort of probe so that we can sort of, from the little trolley, see what the motions are that the person's applying while they're collecting this data, right? And so you can see this is kind of what it looks like. There's no audio for this right now. I think there might be audio on the next slide. But so what we want to do is we want to be able to differentiate between leaves, twigs, and trunks. And oops. It's not going, there you go. And so, this is sort of looking at the frequency spectrum of different signals where we're interacting with leaves and twigs and trunks. And we've begun looking at actually, analyzing the data. Down here on the right, we have a PCA analysis looking at some of these samples. And obviously you can see that, the trunk is fairly distinct. Twigs and leaves tend to be a little bit closer. There is a bit of an overlap, I would say. But this is very promising in terms of being able to kind of differentiate between these different parts of the plant. Is there a question? Okay, I guess not. All right. Oh, all right. Sorry, there are audios. So you can hear, for example, the leaves. Can you hear? Or am I the only one hearing this? Can people hear the sound, or
is that I don't think we're hearing it, Oliver.
No, okay, okay. All right, I'll just keep going then. That's fine, sorry. Okay, in the chat. Oh, okay, no. All right. Okay, what am I doing on time? Oh, okay, a little bit more. All right, so that was kind of looking at interactions, in particular how we can sort of exploit interactions for learning representations, and also doing vibrotactile sensing. The next part of the talk is going to be looking at scope. And so we're really interested in sort of thinking about how we can sort of take this, complicated scene and focus on the parts that are relevant. And also thinking about, when do we need to use learning, when can we use different kinds of models, and effectively when and what to learn. So the first thing I want to talk about is preconditions. So I'm a huge fan of preconditions. Some of you might know about preconditions from sort of classical planning approaches, where effectively, if you want to perform an action, you need to fulfill the preconditions, and then if you perform the action, you'll get the desired effect, right? So effectively, if I want to open up a door, it's important that I'm actually standing in front of a door and have my hands free, so that I can execute the skill, right? If that's not the case, then there's no point in even trying to execute a door opening skill. And so I find preconditions interesting because I really see them as a way of representing the capabilities of a robot, right? So here we have effectively a classifier that's sort of saying, these are all the different situations in which this kind of a skill policy can be executed to get that desired effect. And what we're interested in as well is sort of expanding that concept of preconditions, not just for skills, but for different kinds of models as well. So for example, transition models. So we might have a simulator or some kind of analytical model of our environment. And in some cases, that's going to be great. It's going to accurately predict, what the effects are. And in some cases, it doesn't really apply. And we may need to use a different model that's maybe more costly, right? And so what we want to do is we want to learn the preconditions of when different kinds of transition models are actually going to work or not. And so in robotics, we have a wide range of different transition models. So we can have analytical models, sort of, manually define. These often tend to be a little bit simpler models, but they can be very, very fast. We might have simulations. So my lab uses a lot of Isaac Gym, but we also use things like VREP and Bullet. But simulations, they tend to be a little bit slower, but they can sort of capture a lot of kinds of interactions between objects. They can work in sort of very cluttered environments. Obviously, they're still not always perfect, but they're often sort of more general than those analytical ones. We can also have learned models. So in this case, we have some additional experience. Often these might be sort of for very sort of niche situations that we want to learn them. We may not want to learn entire simulation, but maybe for certain kinds of interactions. These can be very fast, but they do have the sort of the need for additional data. And so as you can see, between these different kinds of models, there's certain pros and cons, right? Some of them are going to be faster. Some of them are going to be more broadly applicable. And we want to be able to sort of balance between these. I should also mention that we don't always necessarily just have one of each. We can have multiple analytical models focusing maybe on specific objects or simulations with different levels of fidelity. But the idea is that we have different kinds of models. And two is we kind of want to create a collage of these different models. So if you imagine, we have our space of states and actions. And for each of our models, we can have certain regions of that state action space where they're applicable. So in this case, we have 3 different models. And this one might be very fast, but it's only certain these blue regions where it's applicable. This might be a middle one that's a little bit broader. And here we have this teal color, a very slow model, but it captures a lot of the area, right? And so what we want to do is we want to be able to combine these together so that we can kind of plan across multiple time steps using different kinds of models for the different skills in order to be able to create a very fast plan that's still accurate while not always relying on the slowest model, right? And so here you can see that we tend to focus on, if the blue one is available, we'll go for that one. If not, then we'll fall back to the red one. And we also have certain situations which are still white here, so some things might be not modeled. So in that case, we kind of just want to avoid those for now. So in order to learn the preconditions, we actually look at first predicting the a distance metric, a deviation for each of our models. So effectively, we provide the robot with a distance metric between states to sort of say, okay, this was your predicted state. This is the actual state that happened in the real world. This is how far apart they were, all right? And so here at the top, we have our transition model taking in our state and our action, or our skill, I should say. We are working right now the level of skills rather than low-level actions. And then we can sort of execute the the same behavior in the real world, and we can get these 2 comparisons, and we can get this continuous value D indicating how far apart they are. What we can do then is we can use that as a way of predicting the deviation estimate in different situations. So we can learn a neural network, or in particular a graph neural network, to predict for different states and actions what that D is going to be. All right, so we can sort of estimate the deviation. So it might be that for a certain situation, we're going to deviate a lot often. So we want to predict that's going to have a very high D hat. And effectively, our model preconditions can then be effectively, any prediction that's within a certain distance. So maybe we allow an error of 2 centimeters so that the next skill can kind of handle that kind of a deviation. But we can also sort of set this later on. And so we first learn this deviation estimator, and then we sort of threshold it in order to create these distinct model preconditions. I should also mention that every time that we have a real world execution, we can run these transition models for all the different models we have, and so we can train a separate deviation estimator for each one of those. So I'm not going to go into the actual method that we use for the planner, but we developed a planner based on our A-star search. It sort of is biased towards going for the faster models, always relying on only those that are actually applicable, and it can also sort of avoid expansions where there's no accurate models. I have the link to the paper. If you're interested in the details, I recommend reading the paper of Alex, but I'm not going to go into details right now. We did evaluate this on a block storage domain. So we had the task of one robot sort of taking so there's a table with 2 rods on it, and it needs to pick it up and it needs to place into one of the bins. We gave it a couple of different skills, so picking, lifting, dropping, lift and drop, and opening drawers. And we gave it 3 different types of models. So we have the simulator model, which tends to be fairly good, although it's not always accurate. So sometimes it sort of jumps through the side, and sometimes it doesn't quite sort of capture the fact that these heavy rods tend to sort of dip down. We have an analytical model that's just looking at the object in the hand, so this rod, and we have an analytical model that's only looking at the drawer. right? So from the three of these, the simulator is the only one that can actually perform the task completely. Although there, like I said, there are certain situations, especially if it grasps at the edges or at the ends of the rod, where it can fail. So here we can sort of see the naive approach where you just kind of assume that the model is correct all the time. Something in the chat. Sensor by attention. Okay. So I got a question from Emma. Emma, do you want to discuss this now, or do you direct message me? I wasn't sure if I should. All right. Okay. So you said that we have to test the sensor. Okay. We have to test the sensor by attaching it to a leaf or a stem. So after doing that, maybe I detect is a leaf. So with the cutting, I know some leaves are hard while others soft. So is it going to have the same speed or accuracy in cutting? To test the sensor by attaching it to a leaf first. So first of all, we don't have, so the plan is not to actually have the microphone attached to the leaf or the stem, but rather have it attached to the hand. So the idea is that even if we have this sensor that we're placing or some kind of a gripper, the vibrations go through the sensor and the gripper, right? So that's one of the reasons I really like vibrotactile sensing is they can sort of do some remote contact sensing. So you don't need to have the microphones right where they are. As we saw on the knife, it was kind of at the handle or on the tongs. Those were sort of the more useful ones. So for the actual classification of, for the cutting when going down and classifying the material, it was actually the microphones on the tongs that tended to be the most useful. And so, we could look at to something like, okay, can we detect whether we've grasped a hard leaf or a soft leaf? So if we sort of have a restriction that, we only want to have sort of fresh leaves that we want to place the sensors on, we don't want to grasp parts that have sort of dried up in the sun, then what we could do is we could sort of, grasp the location there. We could use the vibrations, does it sound crunchy effectively or not, to detect whether it's a suitable placement, and then apply the sensor if we think it is a suitable placement. And so I would expect, and in terms of the speed, like we saw, it doesn't require a lot of data. Passing it through the network is very fast. So, if it's crunchy, there might be the more speed for sort of, re-grasping multiple locations. But the actual detection about whether it's crunchy or not, I would expect to be fairly similar speed.
Thank you very much.
Okay, great. All right, so as we saw in this video, so it's kind of hanging down. So the simulator often predicts that's kind of going to still be upright, but in practice it sort of hangs down. And so if we sort of use the model preconditions, it effectively learns to avoid those kinds of situations and actually can properly insert it, as we'll see here. Thanks for the question, Emma. By the way, that's, yeah. All right. Now it does slightly, when it drops it, hit the top of the container, which might not be ideal, but in terms of predicting the effects of the overall outcome, this is a lot more accurate. And it does sort of correctly predict that it's going to end up inside of the container. We can also see the benefits of sort of, using these different kind of models in terms of a speed up. So if we sort of use our multi-model approach, the planning speed is about 3.7 seconds, 88% success rate. If we only use the simulation, we get a slight improvement in the success rate of 90%. But obviously the planning time, because of those very slow those slow action evaluations, we do get a significantly longer planning time. And so it is definitely a benefit of only using the complexity of the model that you really need in order to make these plans predictions. And we also compare to random models, which doesn't work very well in terms of success rate, so 50%, and has a medium level speed, as one might expect. So, there we have this idea that we want to be able to switch between different kinds of models, but in some cases, it's just very difficult to model a certain aspect. And in that case, what we often want to do is we want to directly learn a skill to. Okay, we want to learn a skill to reach the a goal state in a robust, reliable manner. So if we imagine our state space, we might have some region where all of our models fail. What we want to do is we want to learn some kind of a skill with, again, some preconditions that we can reach, and then transition over to the goal state. And so this is what we did for this project. So we start off, we have our model of the task, we have our planner, it creates some plans, and we can start by just executing those plans. And we'll again going to have a deviation detection. So we see when does that an error occur, or deviation between what we predict and the real world. And whenever that occurs, we do a couple of things. So, okay, first of all, here's some examples of where that might happen. So we might have a misalignment when we're doing this slot insertion task. The handle sometimes twists, or we have an orientation misalignment, or again, the twisted handle. So what we're going to do is we're going to take those situations and add those to a model validity classifier. So effectively, this is like our precondition models of the model. So we know that these are regions of the state space where our model is going to fail if we plan to go through them. We're also going to request a demonstration. So in this case, we're relying on a human to provide demonstrations. We do this using a joystick effectively. And those demonstrations are going to give us two things. First of all, they're going to move to a starting location for the skill, and then actually execute the skill to get to the goal state. So we can use those to learn preconditions for the skill, as well as the policy, so the controller. Once we've done that a few times, we have the skill now, or in this model. At test time, we can again start off by taking our model, putting it into the planner. And once we have a plan, we can pass that through our model validity classifier, see is everything valid? Do we expect all these transitions to happen as expected? If that's the case, then great, we just execute it. But if we predict that it's going to have an error, then we're going to use the skill that we learned in order to solve the problem. Right, so we're going to take our skill precondition, make that be our new goal state, and then replan to that goal state, or that precondition. At that point, we can execute our skill policy and then hopefully get to a nice insertion, as you can see here. So you can see what this looks like in practice. So here, this is the training stage, robots grasping the object. It's moving into place. It detects that there is a misalignment that was not expecting. A person's taken over, brings it to a precondition state, and now acts to move it into the slot. And at test time, in this case, it's already created one plan that it knows this isn't going to work. It's now going to try to go to that precondition, avoiding the obstacle along the way, and then it can reliably insert it. And here we can see some of the results. So on the left, we have without obstacle. On the right, we have with obstacle. We tried sort of using just a DMP, which again was the skill parameterized skill representation. We used just the planner all the way, and we use our approach of sort of combining the planner with this additional skill that I can learn. And we have successes means that it's fully inserted. Partial success means that effectively got to the hole but couldn't insert it. And a failure means it couldn't get to the hole or it hit with the obstacle. And as you can see, we already have a very high success rate using our approach without the obstacle. Also with the obstacle, we get fairly good performance. The DMPs tend to fail quite a bit there. And I think one of the key lessons here is that because we're sort of defining, we're really having the robot request a demonstration only when it needs it. The robot is really learning a fairly niche skill, right? It's a fairly small region. So a lot of the situations the planner can already innately handle. And it's all about figuring out, when do we actually need it to use learning? And by doing that, we create this very, small scope skill, which we can still use on, very different situations. But we can also learn it fairly efficiently, right? So we get a success rate of like, 19, so around 95%, using only 20 demonstrations, right? Already with 5 demonstrations, we get quite good performance. And this helps to avoid having to get demonstrations for every possible state, and really, requesting it only when it's needed. And I think that's a valuable lesson. Actually brings me to another result I really like about this project, which was door opening. So we had a student create a sort of a model of a door, and it turns out that we didn't need to do any learning. So we've been kind of exploring some learning methods for door opening, but it turns out that in this case the robot could kind of perform the task without any assistance. And so I always love this result because, we always think about how we can use learning, and it's nice to sometimes have the robot just say, it's okay, we don't need to lose learning, I got this. In terms of sort of, future work kind of going into the agriculture domain, we are thinking about applying these directly to plants at some point. So obviously, some parts of the plant might be easier to model than other. So in some cases, a simple spring and damper system model might be efficient, for example, of a stem. But if we're interacting with a leaf, then maybe we need some kind of a particle base or learned model, and trying to figure out when we can sort of, switch for each one. And similarly identifying, when is a skill really needed. We're also thinking about sort of, if we have these sort of plant structures, these tree-like structures, looking at the preconditions also of individual parts of that. So can we predict when certain parts of a plant need to be modeled versus just treating them as rigid, in order to reduce the computational cost, and just focusing again on what are the important parts that we need to model and sort of simulate at any given point. So looking at the time, I'm just going to quickly wrap it up. So looking at learning when models are applicable for making predictions, and focusing on sort of learning those difficult subtasks, rather than trying to learn for all different situations, so that leverages both the planner and the demonstrations as well as possible. And with that, I think I'm at the end. I guess one video I could still show. So this is a collaboration. So on the hardware side that we're also I'm very excited about is we're looking at a delta gripper. So this is 2 fingers, each one has 3 degrees of freedom. We're looking at sort of dexterous manipulation. And so this is worked together with Professor Zain Temel, who's done a lot of work on these sort of small scale delta robots. But we're sort of also always looking for additional applications for this kind of work. So just wanted to plug that in there. Are there any questions? I realized that I kind of went all the way up to time. I'm glad to see that some people ask questions in between.
It's a really great talk, Oliver. I really appreciate it. I'm sure there will be a lot of questions, and probably get emails and maybe future meetings. But
Sounds
maybe
great.
we could take one question if someone has a burning question that you want to ask Oliver right now.
I have a quick question for Oliver. Thanks for the interesting talk. When you have to pick models, right? So what if the boundary of you pick a model, you have say 2 models that you can essentially select from, right? So analytical model or simulation. What if the edge case of the boundaries of both overlap at the point that you are interested in? So that's a edge case, right? So what do you do there?
Right. I think this kind of goes into the question of sort of capturing uncertainty maybe in the models. So right now we we have these sort of preconditioned models, but ideally we sort of capture also when are we sort of uncertain, right? So if they're both very sort of close to the boundaries, you could always sort of say like, okay, I'm going to choose the one that's slower just for additional robustness. So if a small change would make that one more viable, then maybe we just say, okay, we're going to go for that one. So I'm trying to think about what the situation would look like. So are we talking about somewhere like the corner here, where it's kind of there's a point where neither of them works?
Yeah. I mean, I understand that that's essentially a codimension one, right? Very few points are there, but I mean, if that's probably an important edge case if something fails, right? So
yeah, so right now it would sort of just choose whichever one is the fastest that it's still within the preconditions. I think, yeah, one future direction is the sort of idea of modeling uncertainty. So if you sort of say like, okay, these are all close to potentially failing, maybe in order to improve robustness, we should just try to avoid this region and try to find a plan that doesn't rely on being so close to this point. And that would require some modeling sort of the uncertainty of the prediction of the preconditions, right? So like a Gaussian process regression has, for example, that built in, you can kind of get it through some dropout or sort of sampling a network like that. But that's definitely a challenging problem, I would say, yes.
Cool. I know, you had a quick question.
Great talk, very interesting. I have a question about the first part of using Fourier transforms to classify, which principles you're cutting and objects and so on. Is there some sort of potential for transfer learning there? Meaning taking, if there is such a thing, even a library of acoustic Fourier transforms, maybe from speech learning and so on, and or speech recognitions, and using that to try and classify the objects you're cutting. Is that something that can be done?
I mean, it's definitely something that could be explored. I mean, I could definitely imagine sort of transfer between different kinds of contacts. I don't know if like speech would be like a good basis for representation. They, a lot of the sounds are very like scratchy, kind of, from like, I mean, it's literally, fingers on chalkboard kind of sounds included in that. But I think, trying to see if there's some kind of like a basis for like, you've interacted with 100 different objects. Now the 101st, can you somehow leverage that? I think there's definitely something, yeah. I think that's an interesting sort of like idea of sort of finding like a common basis between these different kinds of interaction sounds. And maybe even some kind of a, modality like, okay, these are good for making contact. So, you have the thunk kind of sound when you make contact, which might be shared a little bit more between other kinds of contacts. So if I'm making contact with a new object. So I could definitely see some transfer there, yeah.
Awesome. Thanks, Oliver. Again, I really appreciate your talk. And then again, I'm sure there'll be, many. I have a bunch of questions that I'll reach out to you offline. Okay, awesome. All right. Thanks everyone for joining, and we'll see you, most of you, hopefully, the next IDA Coalesce track seminar. Thank you very much. All right, take care.
Thanks, everyone. Bye.